Okay, hi everyone. Let's see. We are looking at section 2.2, which is functions and their graphs. So we're going to look at behavior of graphs, some local extrema or relative extrema, which is aka max and mins. Look at symmetry, whether functions even out or neither, looking at piecewise functions, and then that difference quotient that I spoke about earlier. So some definitions. We are increasing, decreasing, constant, pretty much what you would probably intuitively think. Increasing if we are going up and to the left, or excuse me, going up as we move to the right. Decreasing is our y's are falling, right? Increasing, we're rising. Decreasing, we're falling. And then constants, we're just flatlining, right? So this just says for increasing, as I move to the right, I am increasing y's. For decreasing, it says as I move to the right, my y's are decreasing. And then of course, constant, we're just that horizontal line. So as I move to the right, all the y's are equal to the same number. So relative extrema, that is just also max and min. Basically what you would think of, right? A max is like a hill, and then a min would be like a valley. All right, so maximum, minimum, also thought of as local. Symmetry is basically if there a line or a point where we could reflect onto it itself. Think of if we had a mirror, would the graph show both sides of a branch, so to speak. Even function. An even function is if we have f of negative x equaling f of x. Odd is if I have f of negative x equaling negative x. Neither is just if it's not even or odd, right? So even, odd, or neither functions really tell us what's happening about with the inputs and outputs. But also in that same line of thought, an even function is symmetric to the y-axis. So essentially, we'll talk about it later, but essentially the quintessential even is like y equaling x squared. So if I could fold along the y-axis here, we would see that the branches, again, if I could draw, would lie on top of each other. So an odd function, kind of a quintessential odd function, would be a cubic. If I can draw, okay. So if this is the point, oops, excuse me, 1, 1, then this would be the point -1, -1. So hence why we talk about inputting the negative x and just seeing what gets spit out. Oops, sorry, you can't see. Let me zoom out a little bit there. Ta-da, isn't that cool? So coming over here to x squared, if this is, say, I don't know, 2, 3, then this would be the point -2, 3. So notice that if I change that x value from its positive to a negative, that we get the same y. And then for an odd function, that if I change this positive x to its negative x, that not only does the y value change, not only does the x value change from positive to negative, but also the y value does. So that's how the 0.11 is also -1, -1. Odd functions are symmetric with the origin. Symmetric with the origin. So I think of it as like one fold versus two fold. So if you were to fold along that y-axis, the branches would lie on top of each other, on top of itself. Here with the origin symmetry, if you think of it as pushing down like a push pin, and then two fold, so fold down and then over. Again, if I could draw, the graph would lie on top of each other. So neither function would be like example of a down here, right? This is an example of a neither function. I can't fold on the y-axis, and I can't do that like push pin two fold and to get things to lie on top of each other correctly. So A is an example of a neither. And then piecewise defined functions, remember back in the day, the old people called it like they saw it. So piecewise defined function is exactly that. It is a function made out of pieces. And then the difference quotient. The difference quotient is a stepping stone into calculus. So all of you take college algebra, so it's not split into like who is STEM, who is not, so you all get to learn it. But this thing right here, f of x plus h minus f of x all over h, that thing is what we call the difference quotient. So when we have a function, I like to say we pull the difference quotient into 3 different pieces, but we'll get there. So the first example is the monotonicity. So basically the behavior of the graph. Where are we increasing, decreasing, or constant? One thing to note that I need you to know is that we describe this in terms of x1 to x2. So it's parenthesis, say x1 to x2, close parenthesis is how you would describe that behavior. And this is because at say like this point right here, 0, 0, I cannot say it's definitely increasing, definitely decreasing at this point. It's like a flex point, right? It's both at once. So that's why we're always using the parentheses. And when we use to describe it, it's like we're describing the x-axis. Where or what chunks is the x-axis having the y or the graph increase, decreasing, or constant? So for A, we would have increasing. Look at my super technical shorthand for increasing. From 0 to 2. And then decreasing from negative infinity to 0, pardon me. And then union to infinity, right? Because notice we're going down forever and then down forever. With this also, you'll probably wonder, how did I know this? Is that you write it like we read a book, left to right, okay? So read graphs like we read books, left to right. So you would always describe kind of as that left to right movement. So I want you to pause the video and I want you to try B. And then when you're done, come back. Okay, yeah, you're back. So here I would have a constant. From where to where do y'all think? Yes, that'd be negative infinity to 0. And then hopefully you got that we are then increasing from 0 to infinity. And again, I want you to note that here we have that solid line or solid dot, pardon me. And here we have the open dot. As far as describing behavior, doesn't matter, does not matter. So to move on to extrema, also another really, hopefully you think, intuitive idea. So extrema, I want you to think of the extremes, that's max and mins. So whenever you see extrema, I want your brain to think max and mins, mins and max. So I hope it's intuitive, but if I said, you know, where is this function have a min or a relative min? And you can even see it's right here, right at that little valley point. So if we say have a min of -1 at x equaling -pi/2, a max of +1 at x equaling pi/2. Okay, so here, since you're describing an extrema, it's like, oh, where or how low, excuse me, how high or how low is that extrema? And then where is it at, right? So think of it as like Mount Everest, right? Mount Everest is the tallest mountain. Say it's feet, an actually bad example. I don't actually know how tall Mount Everest is. And then you would say it's feet, and they'd be like, oh, where is it? In Nepal. Okay. So, well, I guess there's 2 sides is part of it in Pakistan. I can never remember. But anyways, sorry, bad example. Think of it as hills and valleys, maxes and mins. In the homework, be really careful to see how it wants you to write it. Does it want it as this min of -1 at x equaling pi/2, or does it want the point? So just one thing that I want you to pay attention to when you're doing the homework.